Okay, good morning, students. Let us begin. I want to go over a couple developments in the area of Exam 2 grades. As you know, it's been kind of an ongoing saga of undoing bloopers. Usually it's student bloopers, but this time it was Dr. B blooping the exam. The regrade that I did for the clicking part, the 3 regular questions that earned you 9 points out of 50, that is done. And I'm happy to say that many of you gained at least 1 point. Some of you went up quite a bit. I saw one student that went from 0 to 9. That was good. All right, so that's a happy situation. Many of you went up. Also, I posted basically this same information, these 2 items, in discussions last night. And I put a picture of a hound dog in there just so you have something to look at, and from Reddit. And I had a student that must have gotten distracted and asked me a question about the bonus point code question. But basically, it's not ready yet, but I'm working on it. And hopefully we'll get that graded and uploaded tonight. And that will be nice because then you'll be able to know your Exam 2 grade, and then you figure out where you stand average-wise for Exam 1 and Exam 2. And that is important because if you have a 90% average or more, then there's a high probability that I'm going to invite you to be a special study group leader. And so those invitations, I hope, will go out this week. We'll organize them next week, and then we'll execute them at the end of next week. Now, 2 Tuesdays from today, we have our Exam 3. And that means the last lecture before the exam is next Thursday. So between next Thursday and next Tuesday, we'll execute special study groups sometime between Friday, Saturday, Sunday, and on up to Monday. And then we'll come in and do the exams together. So we'll get those rolling for hopefully by the end of next week. You will sign up for a special study group inside Web Courses if everything goes according to plan. And hopefully that'll work out well. Last thing to mention about exams, and this is specifically about midterm 3. I've had a lot of students call me up and say, Dr. B, I have plane tickets to go home for Thanksgiving, and I have to take the test early, or I have to take, makeup. No, there's no makeup, there's no early test, there's no makeup, there's no late test, there's no makeup. There's the test. On the syllabus, that's it. That's what we must do. All right, so if you've been here for the first 2 exams, and you have to bail out for Thanksgiving, Exam 3 is going to be your dropped midterm, which is going to be maybe leave you with a little bit less pointage, average-wise, than you might like. But, I have first priority, and from the very first day of the semester, I told you not to do that. And so I'm not going to budge. Don't even bother asking me about it. Just know that your dropped exam will be that Exam 3. Now, most of you will be here, so that'll be good. All right. So, and that's what you want. That's what you want to be. And the reason I emphasize it being here for all midterms is because usually students increase in performance from the beginning of the semester over here to the end of the semester. They're up here, usually, or many times. And so on average, that's what I see. And so I always encourage people, hit all the midterms. And because the last two are probably going to be the two that you keep. But if you have to drop the last one because you're going up to, Schenectady, New York for Thanksgiving with Grandma, okay, but you're going to be stuck with your first two grades, which might be a little stinky. But that's the way the cookie crumbles. Any questions about this? All right, get your clickers out, and we're going to do some clicking together. And we have a huge amount of stuff to cover today. We've got a very full lecture, so don't get up to dismiss yourself until 12:45 or until I dismiss you. Yeah, 11:45, and not 12:45. Okay, what I want to review with you is a brain burner from homework 16 over the weekend, the mixing problem. And this one, I'll just tell you right now, you're going to have it again tonight in homework 17. And you're going to have some more heat, melt, heat, and probably a few more new stuff. But I want to emphasize that these things are good workouts for your brain, and so I want to have extra practice, and that means you're going to see them again on tonight's homework. All right, mixing of two liquids. Let's say that we have two liquids in this simple example. One of them is hot at 333 Kelvin, and the other one is a little colder at 288. So substance H and substance S. And I'm just kind of making this up, just hypothetical substances. These are nice round numbers. And make a note, go ahead and sketch this, two blobs. The temperature gap is the thing that you've got to deal with. And in this particular example, the temperature gap is 45 Kelvin. And the reason that that's important, Aubrey, is because this set of questions, the final question was, what's the equilibrium temperature? Now, the equilibrium temperature is going to be somewhere, in this example, less than 333 and above 288. So it's going to be in that 45 Kelvin gap somewhere. And where exactly they match, that's what you've got to figure out here. Now, the first thing that you know is they're different substances, so gram for gram, they have a different specific heat, and that means gram for gram, it's going to take 1 calorie to heat them up by different amounts. So the same number of calories gained or lost is going to lead to different temperature changes. And so in this example, I just took two nice round numbers, 1.2 calories per gram Kelvin and 1.4 calories per gram Kelvin. And these are imaginary liquids. I don't know if there's an actual liquid with that specific heat, but let's work it out as if there were. And if a real liquid might have a specific heat of 0.92 or 0.88 or something like that. Just do the math the same way. But these are nice numbers, and so hopefully they'll be friendly to us. All right, so they're different substances. So a calorie that substance H loses, because it's the hot one, it'll lose calories. It's going to cool it off by a certain number of Kelvin. But you might have a totally different heat up value, a completely different delta T for substance S, because it has a different specific heat. Matter of fact, which one of these is harder to heat up? Substance H or substance S? Raise your hand if you vote for substance H, harder to heat up. Oh, I see a bunch of chickens in here. Okay, I'm not even going to ask for a show of hands that vote for substance S because I'm taking it that that's everybody. Everybody votes for substance S, harder to heat up. That is actually correct. Because it takes 1.4 calories to heat up 1 gram by a Kelvin. Now that brings us to another thing here. What happens if they have a different mass? So in this example, and in the homework, you had different masses for these two substances. All right? And so let's do some nice round numbers here, 40 grams and 75 grams. You know, if you were a laboratory scientist working for CSI New Orleans or some cool outfit like this, you might have some unknown substance, but a really small sample of it, you know, a milliliter. But they have devices that can figure out the thermal characteristics, and hopefully by that you can identify the liquid. And there's other tools that they use for CSI. This is one of them. Okay, so everyone has a different mass, and so there's another reason that you might have different delta T's, Austin, for the same amount of calories. And the reason that that's important is because if in this physical setup where you have a blob of H surrounded by a bigger blob of S, every calorie that H loses is going somewhere, and the only place it can't go to Dubuque, Iowa. It can't go into your wallet. It can't go onto your debit card so you can buy nuggets, chicken McNuggets at McDonald's. Okay? It only goes into substance S. All right? And so what substance S, so calorie for calorie, you know, substance H is losing a calorie, it goes into substance S. But they're going to have different delta T's. So one of them might be coming down quite a bit easily, and the other one is warming up, but it's tougher to warm up. So you got to work all these things out carefully. Now here's how you do it, and you know this. Q equals MC delta T. Now in this one, the strategy is to say, all right, let me take one hypothetical calorie lost from substance H. How many kelvins does that dip the temperature? All right, because I know if I have a -1 calorie, that means heat lost from substance H, I'm going to get a delta T that's negative. All right, in other words, I'm dropping the temperature a little bit. And how do you figure that out? Well, you just use the MC delta T. Okay, we'll see afterwards. You use the MC delta T formula, and you can kind of see it here in this yellow box. I didn't write out the symbols MC delta T, but I did write 40 grams for the mass of substance H. And I did write 1.2 calories per gram Kelvin for C, for substance H. And delta T subscript H, I don't know what that is, but I'd like to. And I can get that if I use this 1 calorie here. And I'm just using 1 calorie. I could use 1,000,000 calories if I wanted to, or 0.001 calorie. You know, if you're in the CSI lab, you're working with a minuscule amount. You might have to work with 0.001 calories. So what is delta T subscript H? Did you guys write this stuff down? Because we're going to do a question on it together. All right. And question number 1, delta T for substance H. Here we go. And here's the same data down here. All this stuff, it's the same from the previous page. What is the temperature change for substance H? For a heat loss of negative 1.00 calories. So go ahead and work out. And the correct answer is up there, if you can see it. Very nice. Good. I see people consulting. Yeah, definitely double check with your neighbor if you're a little bit nervous. Buffalo Bills. Did you hear who they made captain for the next game? That IK guy that punched Geno Smith in the jaw. He's going to be. Yeah. No, you're TOAST. But everybody's got a lecture or two to burn, so it's your lecture to burn. 30 seconds. It turns out you're a super genius. I can hear everything. No, but see, I can tell from your data if you're a super genius or maybe a sub genius. No. But don't forget, there's some really nefarious characters in literature that are rated super geniuses. For instance, Wile E. Coyote, super genius. No. He always catches trouble. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. I guess we have a little bit of splaining to do here. The correct answer, of course, is oh boy. This is the correct answer. This doesn't have a minus sign here, down here. But that's the correct answer. If you voted for 48 or negative 48, C or D, you're in the right. You're not in the right ballpark, but you're kind of in the right neighborhood, because this pair of numbers down here, that multiplies out to 48. All right, so that's 48 calories per gram. So the calculation is minus 1 calorie divided by that 48 calories per gram. Go ahead and jot this down if you got it blooped up. All right, it's a fairly simple calculation, and you've got to do this. And the other thing is, you've got to figure this out for the other substance. So let's tackle substance S, question 2. Let's see if you guys can knock this out of the park. You know, the amount of stuff that you guys learn in this class is sometimes it amazes me. Don't you think, Nisha? I mean, they have a lot of stuff to learn in here. You guys are. I love teaching this class. You guys are great. You're very inspiring. See, now that's exactly one way to knock out half of the options by asking and answering that question. You know, does it have to be positive or does it have to be negative? You know, for this problem, anyways. Yeah, gain is a plus. Uh-oh, looks like I misspelled the word heat. Two T's. Thirty seconds. 10 seconds. 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what we got here. Uh-oh. We got some difficulty. Oh, boy. So now this is a little bit different kind of a mix. Now a lot of you selected the right value but negative. B is wrong, and I was just talking with a student over here to the right side of the room. This is a gain in temperature, and substance S is warming up. So you've got to have a positive number. So if you got this option B, that's what you forgot. You forgot your, the actual heat process, right? So there's your answer, 0.00952. And here's the calculation: a gain of +1 calories divided by 105. 105 being the product 1.4 times 75 again, just like the previous one. All right, so substance H is dipping and for each calorie of exchange, and substance S is raising. So for every calorie exchanged from substance H to substance S, the initial gap narrows. All right, so you start out 288 and 333. Total gap of 45. Now you're 0.03036 Kelvin closer together after you exchange 1 calorie. All right. Now, you don't have to exchange calorie for calorie. You can go for every 1,000 calories. So let me ask you the next question. If you narrow the gap by 0.03036 for 1 calorie, how many do you get for 1,000 calories? And here's question 3. The correct answer is up there. Thirty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, we got a bunch of votes. Let's see what you guys voted for. All right. Most of you guys got it right. This is, for those of you that voted for option B, that's the correct answer divided by 1,000,000. In other words, that's dividing 0.03036 by 1,000. You want to multiply it by 1,000, and that'll get you 30. All right. Close this. So now here's your strategy, and I want you to jot this down, because your homework 17 tonight is going to include another go at this. It might be a different set of liquids. Matter of fact, I might set up this set of liquids and have you work out the gap. But you're going to have to figure out an equilibrium temperature in this style of problem. I'll probably put a heat melt heat on there as well. Did you have a question over here?
How did you get that 0.0306 number?
Okay, the question was, how did I get the 0.03036? The answer is that when substance H dips down by, I think it was 0.020833, and substance S goes up by a certain amount, a slightly different amount, I think it was smaller, the sum of those two deltas, if you make them both positive, okay, it means that your gap is narrower by a little bit, all right? So basically what you've got to do is narrow the gap down by 0, so you can go calorie by calorie, or 1,000 calories by 1,000 calories, and you can do a table if you want. Now, if you use a 1 calorie per transition, you're going to have a huge table. But if you go 1,000 what was it? It was 3 the 1,000 calories was 30 Kelvin. 30. What was it? 30.36. Yeah. So that's probably a little bit too big. So you might want to go 500 calories. You know, that'll give you a few steps, and you'll be able to figure out, or maybe 100 calories, a few more steps. But 1 calorie is probably too large, or excuse me, too small. All right. I want to check the spring force item. Hit your refresh key on your calculator. The hanging oscillator, the die-hard problem, there were some students that sent me messages inside web courses. They didn't text me on my phone. They sent a message through the inbox system in web courses. And they said, Dr. Reed, what's with this problem? So let's look at it. And you're going to do this calculation again. So consult with your neighbor, and let's try this one out. Hanging oscillator. So it's the same basic thing, except you don't have a die-hard battery. You've got a block of chuctanium, 4 kilogram block of chuctanium. But your delta Y here is 20 centimeters, negative 0.20 meters. So go ahead and calculate that to the nearest. And don't forget, you guys, your spring constant is a positive number. I have a downward delta Y, but that means my spring force is upward. The spring is pulling that weight upwards. 1 minute. Do not mess it up. Remember, the value of K is a positive number. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Most of you got it correct. Looks good. Let's analyze the forces, the vertical forces on this block. So the reason that we're doing this is because I saw students saying, well, what's the formula? And I don't like responding to questions like that. What's the formula? Because if all you know is a formula, that's like being an engineering major, and that's not that helpful. Well, I mean, they memorize everything over there, but how much thinking do they do? That's not what they're trained to do. So let's kind of analyze the forces here. So go ahead and put a dot over here, right here, at the center of mass of that Chuck-tanium block. And actually, I'm going to move my dot over here to the right a little bit. And we know that there's a weight force on the block. So there's a downward weight force. We know the size of it. It's 4 kilograms times negative 9.8 meters per second squared. And so that's a negative 39.2 newtons. Negative sign indicating downward. And that is significant because delta Y is a downward delta Y, so we have to handle that carefully as well. It gives me an upward spring force. So go ahead and make an arrow with its tail on that dot, girls. Okay? But make it the same size, but upward. All right? And I made it red down there on the right. So, although it doesn't look very red on the screen, sorry about that. Now we know how to handle that. Here's the delta Y right here. From the old equilibrium without a weight to the new equilibrium, delta Y is negative 0.20 meters. That was part of the setup, the given information for this problem. And the net force is simply the sum of these two forces. Now, here's my weight force, negative 39.2 newtons, signifying downward. And it's equilibrium, so it has to be equal to 0. And the only thing that it can equal it up to 0 is this baby over here, minus K times delta Y, the displacement from equilibrium. All right? And so this is the new equilibrium. And so this is going to allow me to figure out the value of K. Now, if you look at this carefully, you'll see that there's a bunch of negative signs in here that I haven't written in. Actually, there's one negative sign that I haven't written in. It's the negative sign for delta Y. But when you put that in and then solve for K, you get a positive 39.2 over 0.20 meters. And that works out to 196 newtons per meter. I saw some students in discussions, what's the formula? Okay, this works every time. It's nice, but, you know, do you know why it works? And I've just gone through the description, analyzing the forces, that tells you why it works. And so on the next test, if I ask you a question, a variation on this, if all you know the formula is the formula, you're SOL, and you're stuck. But if you know how to think your way through this one, then you'll hopefully be able to think your way through the variation I throw at you, the curveball I throw at you on exam 3. So your Chuck Norris approved answer, 196 newtons per meter, that is how you get it. Any questions about that? Okay, let's keep going. I want to do a demonstration up here, and I'm going to keep the podcast going, but I'm going to turn the lights on. Nisha? We're going to demonstrate a wave effect and we're going to use this spring. It's a little bit like a slinky, you know, it's not very stiff. It's pretty, you know, flexible. And we're going to wave it, you know, around up here, and we're going to set ourselves at a specific distance. Nisha's going to be a fixed endpoint, okay? And where she stands, she's going to hold it really tight. And I'm going to move the other end at a certain rate. And we'll just stand here. Hopefully these guys can see. All right. Now, so you're gonna maybe want to make a sketch of the waves that we produce on this. Now, see, so I'm just gonna give it a squiggle. Now, watch what happens. All right. Watch the squiggle. It goes out to Nisha and then back towards me. All right. But I'm just sending one squiggle. Now, what happens if I send more than one? I get a different waveform. It looks different. All right. So what happens now if I send? Nice. I saw a student up here going like this, you know, and looking at the thing. It's great. I love that. So what happens if I send them at a different rate? Well, let me try this rate. Squiggles are going out. They're reflecting off Nisha. Go ahead and sketch this. See if you can sketch it. Put a dot for Nisha and a dot for Dr. B. And then, like, sketch a strobe photo. When you catch it at the top and when it's at the very bottom. This, my wonderful students, is a standing wave. It is called the fundamental mode of this spring system. The distance between the endpoints and the stretchiness of the spring controlling the nature of this wave. Okay, so kind of make a sketch of that. Now, I'm going to change my rate of speed again. Let me just let it calm down. All right, Tyler, so let's try a different rate. All right. Now, I'm not... Ooh, I got right to it. Look at that. Faster or slower than the first one? Okay, make a note of that and try to make a sketch. This has one dip and one bump, or one bump and one dip. And the bump over here on my side oscillates. Oh, did I say the word oscillate? Yes. It oscillates between being a bump and being a dip. And then the dip on Nisha's side oscillates between being a dip and a bump at the same rate. So when one of them is a dip, the other is a bump. Now I'm going to move over here so these guys can see it. Okay, over here. All right? All right? Now, this particular higher rate, this wave, is called the first excited state. The first one we saw was the fundamental mode. This is the first excited mode. If you were talking about sound waves, you'd be talking about harmonics. All right? All right, now let me let it calm down. Who was it? Huh? Really? Ooh. All right, now, let me try it again at a faster rate again, even faster. All right? Now, see, if I don't get exactly the right rate, it's just all discombobulated. But this thing's old. Let me try this again. All right. If I get it, there it is. You see it? You see it? What do we got? 3 bumps, right? No. 2 bumps and a dip, or 2 dips and a bump? All right? So try to make a sketch of this in your notes. And those of you with computers, forget about it. People with pencil and paper have the advantage today. All right? Students, this is the second excited state. The third wave mode, also known as the second excited state. All right, let me see if I can get the next one. This is a tough one. Those of you that aspire to greatness, perhaps one day you can. We got it? There it is. Third excited state. I'm not going to move. I don't want to stop. But my hand is getting tired. Okay, that's the third excited state. 2 bumps, 2 dips. Or 2 bumps, 2 dips. Or what did I say? I mean, vice versa, or whatever I meant to say. All right. You get that in your notes? All right, thanks. Thanks, Nisha. All right, now let's go back to taking notes. I have a public opinion survey question to ask you. Here we go. Now, I typed up this question figuring that Darian would still be here, but it's really going to be about the distance between Dr. B and Nisha. Here it is. Between Dr. B and Nisha, you saw a standing wave looking like this. This is the first one. How would you phrase it? Half a wavelength, full wavelength, or 2 wavelengths? Now, I'm going to give everybody points on this, no matter what. It's a survey question. But try to make a decision based on what you think you see and what we know about waves so far. "30 seconds. "10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Interesting. Actually, this is kind of an interesting Fourier spectrum, too. All right. The correct answer is half a wavelength. And the majority of you voted for that. if you voted for a full wavelength or two wavelengths, a full wavelength, make a note of this, would be one bump and one dip between Nisha and me. That would be a full wavelength. Or one dip and one bump between Nisha and me. Now let me get rid of this diagram here, this graph. All right. Now, the general term for what you just saw is interference. Standing waves are an example of interference. And these waves interfere. The ones that I send out from me towards Nisha interfere with the waves that come back from Nisha toward me. Let me repeat that. The waves on the spring that I send toward Nisha interfere with the waves that are coming back from Nisha toward me. And they produce those patterns. All right? So you have to have two sources or more in order to get wave interference. The waves move out independently from the two sources, and the secondary source in the demonstration that you just saw is Nisha. She is like a little source of wavelets over there at her end of the spring. Okay? And what happens is a wave from Nisha on its way back to me and a wave from me on its way out to Nisha, if they meet at a certain point and it's two crests, then you get a super big crest. Out in the ocean, you might call it a rogue wave. Down at the beach, you might call it a really nice wave to surf. Now, you might get two troughs that meet at the same point. And where you get the two troughs meeting at the same point, you get a super deep dip, you know. And that's what you saw. You saw a big trough and a big bump, a crest and a trough in the in the first excited state. You saw one of each. In the fundamental mode, you saw a crest oscillating with a trough. All right? Now, that is what we call constructive interference. When two waves meet, you know, peak to peak or trough to trough, you get an extra big peak or an extra deep trough. Now, if they don't meet eye to eye, if they don't meet trough to trough or crest to crest, you might get no wave. So where you get a crest and a trough meeting together, you get flat water if it's out in the ocean. All right, and that's what we call destructive interference. Okay, the waves appear to destroy each other, but they don't really destroy anything. They don't stop. They keep going, but what we see is a null surface or a flat part of the ocean. All right. Now, here's a couple pictures you could probably diagram. The first one is going to be constructive interference. Okay, so here's diagram one. Wave A and wave B are approaching each other. One from the right, one from the left. And where they meet, the fancy word is they're in phase. So crest to crest. At that part of the ocean, you would get a rogue wave. If these were electromagnetic waves, you would see a very bright flash of light at that point. All right? Now, after they interact out in the ocean, do they stop? No, they keep going on their merry way. So wave A is traveling to the right, and it continues to travel to the right. Wave B was traveling to the left, and now it leaves behind zippity-doo-dah. You know? Question?
So the slide before, they explained the waves going
Yeah, and they're still going, here it is. Okay, A is going rightward, B is going leftward, right?
And then, wait, so,
And then when they interact, that's A plus B.
oh, it's not a wave happening underneath.
Yeah, these are kind of idealized bumps in the ocean.
Okay.
Excuse me.
So these two waves become the second wave, right? Because I'm thinking like,
Yeah, that's right. So that's photograph number 1, and then an instant later, photograph number 2, and then down here's photograph number 3 at the bottom of the screen now. And B keeps going off to the left, off this way, and A keeps zipping off to the right at the same speed. All right, now that's the way constructive interference works. It's a really idealized view. It's one-dimensional, and in reality, waves are four-dimensional, 3 spatial dimensions in time. But this gives you kind of an idea of, the basic idea of wave interference. Now, here's destructive interference. So skip a little bit of space, write the word destructive interference out in the ocean. Here they are. A wave crest, A, and a wave trough, B. The wave crest, A, moving to the right, wave trough, B, moving to the left, and where they meet is flat water, or, as we would say in fancy terms, zero amplitude, but only for that instant of time. They do not destroy each other. They appear to destroy each other. And you would say that they are exactly out of phase. As a matter of fact, if you want to be really fancy, you could say that they're 180 degrees out of phase. One is up and one is down. And at that point where they intersect, their phases are opposite. The water is flat. The interference is destructive. Now, okay, here's the third snapshot coming up. Okay, you ready? There's the third. Wave trough B just keeps moseying off to the left. It doesn't bounce off the other one. It doesn't get destroyed. It doesn't go to Dubuque, Iowa, or anything like that. It just keeps moseying on its way. And this is the cool thing about waves. It's energy being transported, but it doesn't act like a baseball. If two baseballs interacted, they'd bounce off each other. All right? But not waves. They go right through each other. And the wave crest A keeps going off to the right. All right? So this is a one-dimensional picture, and diffraction that we have seen, the picture of diffraction in the ocean, that was basically two-dimensional. Two-dimensional array of waves that had the interference effect known as diffraction. Now, I want to show you another interference effect that it is important to know about. Now, if you've ever driven up the highway, and I know all of you are very nice kids, you're very nice young men and women, you always obey the laws in every way, you never have seen this guy, but and I have to admit, I got nabbed a couple summers ago. It was the day after my last final, so I was totally, I was, during finals week, I'm like, and just like you guys, adrenaline 100%. But then when everything's done, all you want to do is crash. So I'm driving home, and I wasn't looking at the speedometer, and I got nabbed 37 in a 25 by a guy like this. Actually, it was a lady officer. Even worse. Even more embarrassing. Because my wife was in the car, and so I got it from both sides. Oh, brother. Anyways, the phenomenon called beats. Beats. If you have two waves that are close to the same wavelength, but not exactly, then you can observe something called beats. And I believe I demonstrated this. I'll try to demonstrate it on Thursday. I believe I demonstrated it on the first day of classes with the other section. What happens is you have areas where you have constructive interference, and so you have a peak. If this was a sound wave and you were standing here, it would be really loud. But if you were standing over here, where there appears to be, relatively low amplitude, you might not hear anything if it was a sound wave. If it was electromagnetic radiation, this would be bright, dim, bright. All right? So it defines a totally new wavelength, totally new wave, when the two waves interfere. So let's do an example. Now, this is a little bit better than that last diagram. These are actually waves that I used, or that I created using a spreadsheet. And I used the sine and cosine function for these. Slightly different wavelengths. Here are the two wavelengths. Actually, let's get the basics down. Here's my sea level up here, okay, that horizontal line, or as we would say, equilibrium, if it's not a wave in the ocean. Okay, so that's the 0 point of sound, 0 point of the electric field, or 0 point of any other oscillating system. Now, I created a hypothetical wave speed, 80 meters per second. So go ahead and jot that down over in the side or something. All right, and I'm going to park mine over here to the right. And I said, all right, I'm going to take two different wavelengths and two different frequencies. So I set this one up to be 106.7 hertz for the frequency on this one, and 119.5 hertz. Very close. You'd probably be able to tell those two frequencies apart. They're pretty low. They're bass notes. You probably would be able to tell them apart. All right? If you heard one and then the other. But if you hear both of them at the same time, this is what you actually hear. All right? You would hear the sum of the two. And those two waves, so if you got one guy in a car, these little guys that drive around like in a Honda or something, and it's a dumpy looking vehicle, but they got like these monster speakers in it, and when they crank up the volume, it rattles their car and it rattles your car. So if you got one guy on the left and one guy on the right, and you're in between, this is what you hear if they're putting out these two frequencies. All right? So here's what it would look. Try to draw a diagram of it. This is what you'd hear. All right? And so what you'd hear is loud over here, and you'd hear soft over here, faint, and then you'd hear loud over here. Now these things are also moving, so what you'd hear is loud, faint, loud, faint. You would hear beats. It would have kind of a thrumming sound, almost like a machine almost, right? And the sailors under the sea use sonar. They use beats and stuff to figure out where the Russians are. And a lot fancier systems than what I got here, but right. So now, how do you figure out the frequency of this? Because this goes from loud to soft to loud again in a certain amount of time over a certain amount of distance, and so it has its own frequency. What is the frequency? Well, the frequency, Kenneth, is F2 minus F1. Just the difference in the two frequencies. Okay? So in this case, it would be 12.8 hertz. And that, my wonderful students, is something you could not hear. Your stomach could feel it, but your ears couldn't register, not even the best of you, because that's below the threshold of human hearing. It's too low. All right, so 12.8 hertz for this one. All right. Now, at the wave speed of 80 meters per second in these hypothetical sound waves, the wavelengths are 0.75 and 0.67. So the wavelengths are pretty close. All right. Now, what's the wavelength for my beats? This is my interference. This is what I hear. You know, how far apart are the loud from each other? The loud peaks over here, left and right. How far apart are they? Well, it's just the wavelength of this beat frequency. So for every wavelength, there's a frequency. For every frequency, there's a wavelength. If you know the speed, and if the beat frequency is 12.8, then the wavelength right here from peak of the loud to the next peak of the loud is 6.25 meters. Quite a bit longer. All right. Now, I've been using the kind of the metaphor, not metaphor, but the example of sound waves, but we can also do this electromagnetically. Radar guns operate on the same thing, except they're working much higher frequencies, much higher velocity for the speed of light. They're working in the order of gigahertz and 3 times 10 to the 8 meters per second, but they can still measure beats. Question here in the front. How did I get 6.25? The way that I get 6.25 is first I get the beat frequency, 12.8, and then V over F is equal to lambda. Okay, so 80 divided by 12.8 is 6.25. Another question. Yeah, V is equal to lambda over F. So figure out lambda, figure out the frequency, okay, 12.8, and then divide the speed by the frequency. So 80 divided by 12.8. Now, how do the cops do this? Well, they measure something called the Doppler shift. If you go ahead and jot down this YouTube address, it's a train that when you listen to it, you can hear as the train goes by you, the train horn will go down in pitch as it passes by you. And you've probably heard that a million times you've probably heard that a million times for sirens, fire sirens and cop cars and ambulances and stuff. But the Doppler effect is something that you can hear for sound waves and electromagnetic waves. And the radar gun uses electromagnetic Doppler effect, which we're going to work on for the next few minutes. Okay, so the Doppler effect is that relative to a stationary system, if you're moving, if you or the source are moving, you're going to hear a different sound. So, for instance, if you have a train horn that's operating at 113.2 hertz, if the source moves toward you, you're going to hear a slightly higher frequency, and that means a higher pitch. Now, for this train coming at you, it's going to seem to be a high note as it comes toward you, and then as soon as it dips past you, the pitch is going to dip to a lower frequency. As it moves away from you, the frequency is going to be decreased, and you hear a lower pitch. Now, what the radar gun does, it's not listening to sound, it's listening to a radar beam. So the radar beam goes out at a certain frequency, and what comes back is either higher or lower than the base frequency, and therefore you can get beats. So their radar gun measures the beat frequency, and then from that figures out your speed. All right? So listen to and it's just in like the first 2 minutes of this video. And there's 1,000 other videos. They're called railfan videos. all over YouTube. And if you listen to them, some of them, the guy in the cab in the train will lean on his horn before he gets to the cameraman, and then he'll keep on it until he's past the cameraman. And if he does that, you'll hear the Doppler effect for sound. All right, so let's look at how they nab you. This is the formula for how the cops nab you. All right? The return frequency is coming back from your car. The sending frequency is what the policeman does. So there's a factory setting for his radar gun, 2.5 gigahertz or whatever it happens to be. And what comes back to you is either higher if you're coming toward the policeman or lower if you're moving away from him. So he can get you coming or going. If you're coming toward him, you'll have a higher frequency radar signal bouncing back, the return signal. If you're going away from him, you'll have a little bit lower frequency, but you just put it into this ratio and unscramble this square root. So here's how it works. This is actually a formula from relativity, the theory of relativity. And the return frequency, it comes from the moving car. The send frequency is the factory setting, or whatever the police officer sets it to for that day. Okay, the speed of light is 299,792,458 meters per second exactly. All right. Then his onboard computer, his little computer chip in there, solves for V. And you guys could solve for V if I gave you some things. It's kind of a pain in the neck, but you could do it. It requires a little bit of algebra, but it's not too bodacious. But for the police officer, he's not going to sit down and work it all out. He's going to have the computer do that. Right? So here's an example. If the gun has a factory setting of 100 gigahertz, that means that his wavelength, lambda, is 3 millimeters. All right? And that's a frequency that's up there near where those guys operate. They don't really publish the frequencies because if they did, you could defeat every radar gun that you meet. You just got to know the frequency. Okay? So now here's an example of the return. Go ahead and write out all those digits. All right? All those zeros and then 26685.132 hertz. All right? Now that's because you are coming toward the police officer, therefore the Doppler shift has given the return signal a little bit higher frequency. All right? But the difference between them is 26,685.132 hertz. All right? And so go ahead and jot that down. There's your beat frequency. All right? And his computer electronics take over from there. And the onboard computer on his little speed gun, it goes to the digital readout, and this is what the digital readout would say. 89.5 miles per hour, thou art busted. Okay? Now, I hope that never happens to you. I hope you're all very nice, good, law-abiding citizens. But if that happens, you're going to be busted. And it's very tough to get out of it because this is a measurement on the order of 267 parts per billion. So it's pretty precise what these guys have. All right? The reason they don't nab you at 37 in a 35 or 27 in a 25 is because they don't want to, but they could if they wanted to. Write down this website. The periodic table, webelements.com, a huge study target for us. But before we get to periodic table, webelements.com, We're going to hack into chapter 7. So you're going to have some homework tonight, and I want you to start reading into chapter 7. Okay, you're dismissed. I'll see you on Thursday.